It starts us into a new chapter, and this chapter is going to be a mini unit, just a couple of sections, but this is one of my favorite topics of pre-calc because what I think is just fascinating on its own, but also I think it's a really beautiful bridge into calculus because one of the amazing things about calculus is that to me, it starts to stretch the bounds of what we've thought math can be and what math can do, and help us reimagine things in ways that might be better for our needs to express things mathematically. And what we're going to do today is called polar coordinates. And the big thing to remember as we start off this is so far, I have only taught you how to graph under one system. Think about it as a graphing language, and that language is the rectangular coordinate system. In the rectangular coordinate system, our coordinates are given in the xy form. The x value tells us how far to go to the left and the right. The y value tells us how far to go up and down. This is standard. This is what you have been doing since the beginning of when we taught you to graph. So if I graph in the rectangular form, let's say I wanted to plot the coordinate point 3 comma 2. Well, I know the 3 stands for the x value, the 2 stands for the y value, so I'm going to go to the right 3 and up 2, and then this is my point. And so at this point, this is all that we have done so far, and we could use fractions, we could use square roots. They don't have to be nice numbers, but it always told us a specific distance to go to the left and right or up and down. Polar coordinate system are still going to start with a foundation of axes that will go horizontal and vertical. But instead of using rectangular, these grid lines, we are going to instead work more in a circular system. And so polar coordinates are given in the form r, this highlighter's tiny, there we go, in the form r comma 0. So rather than x comma y, we have r comma, it's not 0, it's theta, sorry, it's been a long day, r comma theta, where the r value is the distance from the origin, and theta, not 0, theta is an angle formed by the polar axis and a ray from the pole. First off, some big words here. Polar axis, that's our 0 degrees positive, where we think of the x-axis, but this is, think back to the unit circle, it's 0 where we start here. And the pole, that is what we call, that's another word for the origin. It's that center point, it's 0, 0, it's where we start. So here's a couple of basics. I haven't actually given you the whole grid yet because we're going to build the layers as we get more comfortable with it. So a couple of things. First, before I explain what these circles are, we're going to switch back real quick to the unit circle, and I am going to cut these out for just a second. Okay, so what we remember from a unit circle is it starts taking this idea of circles and all these different values and combining together xy coordinates with angles and with the circles. So the one thing here is this unit circle is only shown with one circle, and it's a circle of radius 0. But we use these lines to represent the angle measurements that we are on. And then the coordinate points actually do represent the xy values that we have. So what we're going to do is we're actually going to say, well, we could work greater than just the unit circle, but use these same angles of reference. So before I switch back, there's a couple of important things here. I want you to remember that the lines that are closest to the x-axis are all going to be the 30-degree reference angle. So it's 30 degrees between the x-axis and this line. And they'll all end with over 6. So 150, it's 30 degrees between it and the axis at 180, and its radian form is over 6. That works with the other lines closest. The middle line is our pi over 4 or 45-degree angle lines. The top line furthest away is the pi over 3s or the 60-degree reference angle. That's going to come and be very important here for us. So next up, I said we could expand it. So rather, instead of just drawing one circle, we're going to start drawing multiple. So the first circle has a radius of 1. Second circle has a radius of 2, 3, 4, so on and so forth. Usually we, just for the sake of being concise, we only draw a couple circles. Let's say I wanted to plot the polar coordinate 3, 45 degrees. Well, let's think about what we know about our lines. I actually just reminded you guys that the 45 degrees is the middle line here. And so any point along any of these circles, any point along this lines will be 45 degrees away from 0. We go 45 degrees to get up to this point. So if I wanted to plot the point 3, 45, what I'm going to do is find the 45-degree line and then count on the circles. This is 1, 45. This is 2, 45 degrees, the third circle. And we'll make a dot there where the line and the circle intersect. This is 3, 45 degrees. So now, instead of just sketching our line in, we do draw them. So I'm about to show you what it looks like. So number 1, this is a blank graph, just like I could give you a grid for rectangular. This is a blank polar graph. I know it looks crazy. Let me show you a couple of important things here. So first off, sometimes I find it helpful just to brief or quickly highlight. That's kind of too light. Let me switch to a better color. To highlight the axes because they get lost in there, so I know where we're starting. So some important things to remember is that 0 degrees or 0 radians is the first line to the right. I go up. Hopefully you remember it's coming back. This is 90 degrees or pi over 2. The next line, and it doesn't want to write for me here, is 270, or sorry, I'm skipping 180 degrees or pi. The next is 270 degrees or 3 pi over 2. And then in between, we have to use our knowledge of the unit circle to know which line to go for from there. So next, let's look at plotting some points. Sorry, one last thing to point out. There's one more line than you might be used to. So just to refresh your memory, our middle line, 45-degree line, is going to be, they're going to be the ones right here. And so then that means the lines 1 over from there. This is the 30-degree or pi over 6 lines. And then one more. Let's do this nice purple here. This is the 60-degree reference angle, or, and I picked the wrong one there, or the other lines for pi over 3s. So you'll notice there's an extra set of lines. Essentially what we did is each of these lines are separated by 15 degrees. So now the best way to, if you're confused, to go between each of them is to just add 15 degrees. 15, 30, 45, why is it hard? 60, 75, and then 90, and then it goes from there. All right, so let's go ahead and plot some of these points. So first off, 2 comma pi over 2 is our first one. So you can go in whatever order you find helpful. I usually like to locate my angle first and then go out to the correct circle. Pi over 2, we've got that mark. That's the vertical. Circle 2 is the radius of 2, so that puts us at 2 comma pi over 2. All right, we're going to skip part B that has a negative right now. We'll come back to that. Right now, for part C, 2 comma 240. Use those quadrants to help you out here. Narrow down the search. 240 has to be in quadrant 3. And that one is closer. It's close to 270. It is 30 degrees away. And then that will put us, let me switch colors. Circle 2, that's going to put us right here along that light purple line in quadrant 3. So that is 2 comma 240. And then lastly, before we go back to what that negative means, we're going to do part D, the polar coordinate 3 comma 150. So that's going to be on circle 3 and then at 150 degrees. So for 150 degrees, let's do some locating. If I were to actually start at 180, go back 15 and go back another 15, that's probably the easiest way. That puts me on that yellow line. And then 3 circles out is the furthest one, and that is the point 3 comma 150. All right, so what in the world does that negative mean? Well, let's at least first do it if it was a positive answer. If this point was a positive 3 comma 0 degrees, that would put us along the line of 0 and then out here at positive 3. So what a negative does in general when we count is it takes us the opposite direction. So if positive 3, 0 is located where my red pointer is, negative 3 is, we can find that by staying on the same line, but going the opposite direction 1, 2, 3 units. And that puts us right here, right on this 180 degree line. So this is negative 3 comma 0 degrees. And it might feel confusing because you might think, wait, that angle is 180. Yes, but if I start at 0, find the angle first, and then flip to the negative, then that flips me over to the opposite side, which is actually going to be that same place as 180. And we're about to talk about the fact that, so could I just call that positive 3 180 degrees? Well, yeah, you sure can. You actually can, and we're about to do that here in this next section as we talk about the many ways to describe polar coordinates. Rectangular coordinate system, what we've seen so far is that every ordered pair represents a unique point. So the dot that goes with the point -5, -7.3 is the only dot, that's the only way to describe that dot using the rectangular coordinates. But in the polar coordinate system, there's actually an infinite number of polar coordinates that represent the same point because we have this idea of coterminal angles that we learned back when we did our trigonometry unit. So what we're going to do is we're going to look at two different points, one with degrees and one with radians, one with a negative, one with a positive r value, and one with a negative. We're going to look at the different ways that we can name the exact same point using other polar coordinates. So the first one is 3, 90 degrees. 90 degrees should hopefully be a easier one to locate. That's our straight vertical line. So this is 3, 90 degrees. So first off, our option is to keep a positive radius of 3 and use a different angle. Well, so there's one option. I could start at 90 and go another positive 360 degrees around, add 360 onto that and see where that puts us. Another method is, remember, we can also go negative angles. So if I go negative 90, that's here, negative 180, and negative 270 actually puts me in the same place. So I could say that this is 3, negative 270 degrees. So let's try to keep these numbers between negative 360 and positive 360. So I'm not going to be able to add or subtract a full circle anymore, but we also have another option of using the idea of a negative radius. So if I was at positive 90 and I went to negative 3, that would put me here. So what I want to think about is what angle happens here, where if I say that the radius is negative 3, then what angle should I go to so that when I flip to the opposite side of the line, it will put me at the same spot? So that's right here where the red dot is. And so at this point, this is 270 degrees. So if I'm at negative 3 to 270, that's here. And then to make it positive, we flip, and that lands us in the same spot. So negative 3, positive 270 degrees is another option for this same point. Let's use one more negative, and let's make it a negative radius and a negative angle. So we're going to essentially figure out one more spot, the same thing at negative 3, 270, but that angle is also the same as negative 90. So this is also negative 3, negative 90 degrees. Let's look at a radian degree and then a negative angle. So a couple of things is with these negatives, remember we're going the opposite direction. I would start by kind of asking myself, is this going to be, it's close to pi, is it right before pi or right after? And this is going to be right after, or sorry, right before pi. And those pi over 6 lines are the ones that I said were closest, we're have to skip a line, remember, but they were going to be the line closest to the x-axis when we skip. So negative 2, so that makes negative 5 pi over 6, this line right here. So if it was a positive 2, we'd be here on the second circle, but we travel that line through the origin. We go out the opposite side, the same place, 1, 2, and that puts us right here. So this is negative 2, negative 5 pi over 6. So let's go ahead and let's kind of follow the order that we did before. So the first thing we did is this time, since it's a negative angle that gets us to this place, we want to think about this line right here at negative 5 pi over 6. What's the same positive angle as that so that I could still use a negative 2 radius? Well, in the positive angles, this right after pi is 7 pi over 6. And if you don't remember that, it's a great time to check your unit circle. Okay, so that's our option of keeping the radius negative. Now let's switch it to a positive 2. Positive 2, well, if it's a positive 2, we don't have to do any switching, we just describe what angle this is. Well, this is quadrant 1. So that makes this angle positive pi over 6. So this is the same as 2 comma pi over 6. Lastly, if we did positive 2, if I thought about from 0, how would I get to this point? Well, from 0, I go all the way around, except just a little bit. And if you don't remember that, that's going to be negative 11 pi over 6. So those are 3 ways to describe this. So you might feel a little bit overwhelmed. What just happened? Silly was just coming up with all these numbers. I'm going to show you actually there were some rules behind what was just happening. Now, I wasn't using the rules. I was just kind of using logic to figure these out, but there are some rules that can help us narrow this process down. So first thing is, let's say we're starting with some basic polar coordinate with a radius of r and an angle of theta. So the first option is I keep the radius the same. So if the radius is positive, it stays positive. If the radius is negative, it stays negative. So what we did in that case, that was usually the first thing we did, is we would go a full circle around. And so that would be either adding or subtracting 360 degrees, or if we're working in radians, that's going to be plus or minus 2 pi. If instead we make the radius switch signs, so it either goes from a positive to a negative, or it is negative and we make it positive, then instead of that, if we just want to go from one point, when I go around to the other point, I'm actually going halfway around the circle, exactly halfway, which is 180 degrees. So this would be our angle plus or minus 180 degrees, or this is the same as adding and subtracting pi. So these rules actually can really help us narrow this down. So what we're going to do is, in this next example, number 3, we're actually going to figure out 3 other points to describe points without graphing. So without graphing, name 3 other points that represent the same point given. Now here's this important part. It says with our theta in the middle here being between negative 360 and 360, and negative 2 pi and positive 2 pi. So here's what's going to happen is, so if I tried to, so for this one, let's keep the radius sign the same and use our rule. If I first tried to add 360 degrees, well, that takes me, 60 plus 360 takes me to a number already bigger. So let's just go ahead and subtract it once. And that puts us at negative 300 degrees. So that's going to be first angle that should be coterminal, be in the same position. So we're just naming this point a different way. So since I can't, so if I subtract it again, that would make it negative. I have to now, so I did one where I kept it the same, and now we have to switch the radius. So if the radius was negative 4, I can add 180, and that's going to be 240 degrees. That's still less than 360, so we're good. And then let's do it one more time with negative 4, because we could now subtract. Subtract 180 from 60, and that is negative 120 degrees. Let's do another one with radians. Same idea, except we're going to be adding 2 pi and pi, and so you'll get a nice refresher on how this works. So first one is, if the sign is negative, let's keep it negative, and we want to add or subtract 2 pi. Again, with these kind of, if you're looking for a pattern, to keep it between these bounds of negative 2 pi and 2 pi, we're not going to add it on just because it will go above that. So we're going to do 3 pi minus 2 pi, and that is 3 pi over 4. Common denominators makes this minus 8 pi over 4. So that gives us negative 5 pi over 4. So this is the same as negative 5 pi over 4. Now let's switch it to a positive r. And from going back to 3 pi over 4, we want to add pi and subtract pi. So that's plus, to make this common denominator, that's plus or minus 4 pi over 4. When we add it, 3 plus 4 is 7, so that's 7 pi over 4. So that's one option. And then subtract it, that's negative 1, so negative pi over 4. And those are our 3 options. The last new point of today, thank you for sticking with this so far. This is one of our longer sections, but it's such a needed foundation for what we're going to continue to do with polar coordinates. And this last thing we're going to do is, I can take a polar coordinate. And let's look back up here at any of these dots. And if I removed the circles and the lines, I'm actually left with an XY axis, and I could figure out what is the XY rectangular coordinate that describes that position. It is still a position in space. It could be described with a rectangular coordinate. So in order to do that, we're going to come up with some rules in order to figure out how to do this. And in order to do that, we need to make a connection between an XY point and a radius and an angle, and we are going to do that using Pythagorean theorem. So here's what we got. We're going to draw a random point out here. I'm going to put it in quadrant 1. We are going to say this point has coordinates r comma theta, and then if I took this point, connected it to the origin, this distance right here will say it has a length of r, and then the theta is the distance between the x-axis and this line. So next up, let's go ahead and drop a perpendicular and turn this into a right triangle where, go ahead and then I'm going to draw the x side over here. So at the base of this right triangle, the distance, that orange distance here, we're going to call x, and the vertical distance we're going to call y. And so this point could be described as r comma theta, but it also could be described as x comma y. So what we're going to do, our goal is to make some equations that will end up working as formulas for us that will connect the radius and the theta to an x and a y value. And we're going to do that using Pythagorean theorem and trigonometry. So to give you some structure here, the first set of rules we are going to do will be the most helpful when you're going from rectangular to polar. So you are given a rectangular coordinate and you want to go to a polar coordinate. So next up, here's what we got. So in order to connect x, y, and r, the best way to do that is Pythagorean theorem, where, and that did not change colors on me, hold on, where x squared plus y squared is equal to r squared. And so if I wanted to use this to solve for r, that means that r is equal to the square root of x squared plus y squared. And this is actually going to end up being one of our first formulas. If I know x and y, I can plug that into this formula and it will help me know the radius of this polar coordinate. So then next we need something to figure out the angle. So again, we want to connect it. And at this point, we maybe don't want to mix it up with r. We just want to use something that involves the theta and the x and the y. So I want you to think about this for a second. What do we do with right triangles and angles, and how do we use those to find sides? Well, we use trigonometry. Based on those sides here, x and y are opposite and adjacent. So that means that the tangent of this angle theta is equal to y over x, or if we want an alternative version, we could use the inverse to get the theta is equal to the tangent inverse of y over x. So this is one of our formulas here. Okay, so then the next thing that we are going to do is get a set of equations and formulas that are going to help us if we're going the opposite direction, polar to rectangular. Any set of these could be used, but this is sort of the easiest process here. So next up, let's say I just want to solve for the x coordinate or the y at one time. I don't want an equation that uses both of them. So in that case, let's look at just x, theta, and r and think about trig. Well, this is adjacent and this is hypotenuse. That is the cosine. So that means here that the cosine of theta is equal to x over r. Let's solve for x. That makes here that x is equal to r times the cosine of theta. And this is going to end up being a super useful formula here. Next up for y, that is opposite in hypotenuse, so that is sine. So that makes the sine of theta equal to y over r. Multiply by r, solve for y. That gives us that y is equal to r times the sine of theta, or we'll sometimes just shorten it to say r sine theta. So let's look at how this works for both directions. And I'm going to shrink these just a little bit. Okay, so for the first one, it says convert negative 5, comma 5 root 3 to polar form. So that means that this is a rectangular coordinate. And I know it looks a little frustrating to have a square root in there. I promise you it will actually make the number come out to be better. So -5, +5 root 3 is going to be somewhere around here. It doesn't have to be precise, but so we're thinking that this r, it's always going to be a positive number, but then the angle will be somewhere in quadrant 3. So let's go ahead and look here. So this is going to give us, if we want to solve for r, we're going to go rectangular to polar. It's the first set. R is equal to the square root of x squared plus y squared. So for our radius, that makes the radius equal to the square root of -5 squared plus 5 root 3 squared. So that gives us 25 plus, and then 5 root 3 squared is, we square the 5, 25, then just comes times regular 3, and that's 75. So that equals the square root of 100, which makes our radius come out to be 10. So that wasn't too bad. So next up, we have the angle. So we have tangent of theta is equal to the y value over the x value. So it's equal to 5 root 3 over -5. Let's cancel those 5s, and that makes tangent of theta equal to -√3. Now comes that time, if you never memorized your tangents, it is going to get a little bit trickier, but if you would like to, you can use your calculator. So if we go to our calculator, we are going to use the inverse to solve for the angle. And so we want to put this, it's probably going to be easier if you put this in degree mode, because otherwise it will give us a decimal for the radians. So we want to do the inverse tangent of negative square root of 3. And that gives us -60 degrees, which is going to be somewhere in quadrant 4. That means that we are going to go here and subtract 60 degrees from 180, and that puts us at theta is equal to 120 degrees. So this all goes back to how we used the calculator to figure these out. We knew we had to be in quadrant 2 based on where we plotted it, so we had to subtract from the closest axis, which is 180. So that makes this the coordinate point 10, 120 degrees. Next up, convert 4, -pi/6 to rectangular form. So it's important to recognize this is in polar form, which means the radius is 4, the angle is -pi/6. So what we're going to do, sorry, that looked very messy, polar. So what we're going to do is, oh gosh, it froze. So what we're going to do is we are now going to use this second step because we want to solve for x and y separately. I don't want to use the other equations because they both involve kind of having x and y at the same time, and that's going to be really messy. So I actually really like these. So this is going to make x is equal to r, so 4 times the cosine of -pi/6. All right, it's time to open up that unit circle. So -pi/6, and here's the thing, I would love if you have this memorized, but if you don't, please use the unit circle. So here's what we got. We're going to go to -pi/6, which puts us at 11pi/6. Cosine is the x value. This would be also if we would review if we were in class, but that is the value of 3pi/2, or sorry, root 3 over 2. So that becomes 4 times root 3 over 2. The 2's reduce, and that makes the x-coordinate 2 root 3. Now let's do the same thing for the y-coordinate. Y is equal to 4 times the sine of -pi/6. And hopefully you remember if the one is root 3 over 2, the other one is 1/2, but maybe we forgot that. And then since it's a sign in the fourth quadrant, it's negative, so 4 times -1/2. And that gives us -2. So that makes our rectangular coordinate x, y 2 root 3, -2. Okay, so next up, what we have for you is some practice on, and this froze, so we're just going to stay here, is some practice for you to do this on your own. I'm going to record some extra problems if you feel like you're stuck and really do need to see more. The closure on here, you're not required to do them, but I will record what that looks like and give you those answers, and you can look at them on the key. Be sure to ask questions or come to office hours if you have help or if you have questions and need help.